Hi, welcome to Quantum Projects, where the matrix becomes reality. Remember back in October when I coded this? No? Well, back in October, I coded this. It's a 2D, 3 degree of freedom flex body physics simulator. It was a fun project, and it was very simple to make. It only had around 300 lines of code, and it allowed for some pretty cool stuff to be simulated. But it was kind of useless. And, I mean, what am I even supposed to do with this? Since I simply can't stand useless projects, I decided to keep working on it. I added a lot of stuff, and now it's actually pretty cool. I call it Physics Simulator 2, or SimMark 2 for short. A few months ago, I released a video detailing my plan to build a custom flight controller for a quad-rotor UAV. The first video didn't contain much, but after I released it, I actually did quite a bit behind the scenes. I built the actual circuit board, the entire drone, and wrote all the software. However, I ran into a pretty big problem. The RC receiver that I had chosen was a serial-based receiver, and the microcontroller that I was using didn't readily support simultaneous PWM and serial functionality. To put it plainly, I couldn't control the motors and receive commands from the pilot at the same time. Now, I know that it is technically possible to do this somehow because that's exactly what Nicholas Dream is doing with his Dream flight, but I couldn't quite figure it out. Which brings me back to SimMark 2. This simulator was built with one goal in mind: to simulate a UAV so I didn't have to build one in real life. But now that it's done, I can simulate a lot more than UAVs. In fact, later in this video, I'll show you how I used it to create a virtual CubeSat complete with autopilot. I created this tool because I know the value of a good simulator. From June of last year to December, I interned at a space company in their Loads and Dynamics group. The core of my work revolved around simulating crucial mission events to ensure their success. Real companies use this technology to make sure that everything works before even fabricating a single part. And now I can do the same with my own personal projects, just in a much sketchier and less professional way. So, let me tell you how it works. The actual physics is simulated in a relatively simple manner. The finite element models being simulated are made up of nodes and springs. Each node has a mass, and each spring has a stiffness and damping coefficient. By summing the forces on each node, I can compute that node's acceleration, and with acceleration, I can take a double integral to get its position. This was about where the fun ended with SimMark 1, which was also only in 2D. This simulator, however, has a variety of new features. Mark II can now automatically calculate the moments of inertia of the loaded finite element model, as well as the net torque applied at any given moment. It uses this information to calculate the model's angular acceleration alpha. With the angular acceleration, the angular velocity and absolute angle can be backed out via integrals, just like velocity and position. I've also added body fixed coordinates. This one was not easy to figure out. In fact, I've been trying to wrap my head around this problem for like 2 years. They're simple enough in principle. Fix a new coordinate system on your object, and now each point in space has 2 different coordinates. The coordinate relative to the origin of your world, the inertial coordinate frame, and the coordinates relative to your body object, and the coordinates defined in the reference frame of the object. They're not so simple in practice though. Transforming from one to the other requires Euler angles and linear algebra. That's right, the matrix is about to become reality. The transformation matrix, because the easiest way to transform coordinates from one frame to the other is via a transformation matrix. Multiplying a transformation matrix by a vector will transform that vector into a different coordinate system, which allows us to easily translate from an inertial coordinate system to a body fixed one. However, to do that, we need to actually find the transformation matrix. Good luck finding any information about that online, by the way.
Your eyes starting to hurt?
No. We do that by taking our body fixed reference frame and figuring out how to spin it such that it aligns with our inertial one. Spinning an object in 3D is really weird and difficult though, so it may be a little easier if we introduce an extremely weird and difficult concept called Euler angles. Euler figured out that any 3D rotation can be broken down into 3 principal rotations. These rotations take place about a body fixed X, Y, or Z axis, and their sequence matters, because once you rotate something once, its body fixed axes move. Let's switch locations. There are 12 Euler angle orders that can be chosen when performing 3D rotations. I chose YXY for my simulator, but the choice really doesn't matter. All that means is that I'm doing a rotation about the local Y axis, then one about the local X axis, and then another about the local Y axis, to line up the coordinate systems. The angle delta between each rotation is known as an Euler angle, and when all three are combined, you have a 3D rotation. Once these Euler angles are calculated, all you need to do is calculate 3 principal rotation matrices associated with them. Then you multiply all 3 together, and congratulations, it's a transformation matrix. The beauty of transformation matrices, or most matrices really, is that if inverted, it changes the vector it was multiplying straight back to where it started. This means if I compute a body to inertial matrix, I can just take its inverse to compute an inertial to body matrix. This is great for me personally because I really hate math, so the less actual thinking I have to do, the better. Anyways, why do we even need a body fixed coordinate system? One word, a lot of reasons. Let me give you an example. And I know that's not one word. Let's say Timmy wants to create a 6-DoF physics simulator and he wants to simulate an airplane. Codes the engine on the airplane to always apply a forward thrust, as is usually the case with airplanes, and clicks go. But when the airplane pitches, the thrust, well, it keeps pointing forwards, but it's not aligned with the airplane. Now, Timmy's really sad because if he wants his thrust vector to stay aligned with his plane, he's gonna need like 800 trig functions to keep that vector properly oriented with the airplane. But wait, if he can just define a new coordinate system on the airplane and define that thrust in that coordinate system, it'll always point the right way as long as the coordinates stay stuck to the plane. Although it's kind of hard to get the transformation matrix that will transform these vectors from inertial to body fixed, once you have that matrix, it's actually really easy to perform those transformations because you only have to do hard math once per time step. With body fixed coordinate systems, it becomes possible to simulate aerial vehicles with their own stationary thrusters like drones or airplanes, whose propellers always thrust in the same direction relative to the vehicle that they're attached to. Did you get all that? No? Great. Let's move on to some demos. I coded 2 of them, and they're really cool if I do say so myself. In them, I'm simulating a CubeSat. It's just a cube, but referring to it as a satellite makes me feel a lot smarter. With 8 RCS thrusters, literally just force vectors, on it. Don't worry, I won't go into the math. Yes, I will. In Demo 1, the CubeSat is subjected to random impulses every 0.5 seconds. These impulses cause the satellite to experience unwanted rolling, pitching, and yawing, which is promptly corrected for. Wait, corrected for? Did I code PID into the simulator too? Yes, I did. The satellite corrects for angular disturbances by calculating its error in roll, pitch, and yaw, and responding accordingly via thrust commands computed using a PID controller on each axis. In Demo 2, I got a little crazy. I decided to simulate the satellite back on Earth with gravity. In this demo, the satellite's going to be given some coordinates to fly to, and then it's going to fly there. There are now a total of 6 PID controllers running. 3 for the rotational axes to keep the satellite stable, and 3 to translate it to the desired point. I really could watch this forever. It's just so cool. Look how quickly it reacts to changes in set points. And it doesn't overshoot the maneuver at all. This is really similar to something else I've seen somewhere, but I can't quite put my finger on it. It's probably not something scary and horrifying. Anyways, those are the demos. Yay. These demos demonstrate that a robust control algorithm can be derived in a virtual environment prior to any actual flying whatsoever. In the future, I plan on using this software to model a real vehicle. Before ever printing a single part or soldering a single wire, I can derive kinematics for the vehicle, tune all of its control loops, and even write the software that'll run without ever risking damaging any expensive components. That is why I wrote this software, and it's definitely not because I would rather do literally anything else than my home.